Hello, DEF CON. I'm actually going to break with tradition this time and start 1 minute early because I have so much shit to show you guys that I'm worried about how much I can fit in here. I have not counted, but I'm reasonably confident in saying that there are more explosions in this presentation than any other DEF CON presentation in history, which is crazy because it's like nearly a quarter century of DEF CON. Can you believe it? That's totally blowing my mind. A lot of projects are not solo, but this one is very much not solo. I called in like so many favors and working on this project, so a lot of friends went above and beyond to help me out. So this is their old school ANSI splash screen, hacker thanks. I think the only person who made it to con this year is RF, so hopefully he's awake and watching. So I was inspired to do this by a talk at DEF CON 19 by Bruce, who just spoke in here, and Deviant and Shane, about they were running some kind of data center that had very valuable stuff on, on the hard disk in that data center, and they were sort of kicking around some ideas like, it could really be a target for some criminals to come and steal everything. So could you have a switch that you could flip to destroy physically all of the disks in your data center? And I thought this was pretty cool, and I really wanted to kind of do a follow-up and do some experimentation of my own. And then 4 years later, I thought about, where are we now? We've actually had data centers be physically raided and have all their stuff stolen, Tor mail, the multiple Silk Roads. And Snowden taught us that we don't really know how much we can trust crypto because our endpoints are so insecure. Your crypto is only as secure as the keys. So think about it. Does the NSA, when they get rid of encrypted drives, do they just throw the drives away? No, of course they don't. They destroy them completely. So here are the goals. Flip a switch, drives are gone, no bits left standing. Protect your data center against highly motivated criminal organizations, such as the three-letter government agencies. And then, of course, the big one, produce a lot of destruction prawn for the DEF CON audience, for all you here. So that means more thermite, more high explosives, and more voltage. So these are the rules that Bruce and Shane and Deviant came up with, and I'm going to mostly try and follow them. You have a 1U server with your equipment in it. You have 1U above and below for whatever you want. I personally, when I was doing this, tried to keep all the actual destructo equipment in 1U so that the other 2U could be used for protection, hot gas extraction, and so on. 60 seconds to completion. I really want to make a joke about Bruce and Deviant and Shane here, but I won't. Don't set off the fire systems. Don't set off the seismic sensors in the nearby banks. I don't really care about that, so don't worry about that. Contain the damage within the equipment and protect any nearby humans. A quick word on hard disk technology. Data centers still use a lot of spinning platters. These tend to be made out of aluminum and now more frequently glass. And glass smashes easily. So most of this stuff is with aluminum. Almost everything I do here will also work on glass. The coating is really interesting of hard disks. They have underlayers of a cobalt nickel iron alloy. The magnetic alloy actually is cobalt chromium with platinum, and these layers tend to be separated by 4-atom layers of ruthenium. So very chemically unreactive, actually, the surfaces of hard disks. And now, of course, not so much in data centers, but we're starting to see solid-state drives, so I wanted to do a little bit of stuff with them too. Here are the results from DEF CON 19. They did 3 categories, and they split it up between the 3 of them. So Deviant worked on incendiary, and their results were they had some regulatory issues with possible deployment because they were working with tannerite, which is used for making explosive targets. And legally, to set off tannerite, you have to shoot it. And they did some melting of the aluminum platter hard disks using propane and MAP gas. And what they discovered was the drive is an excellent heat sink. It's a big chunk of cast aluminum. The platters themselves, often aluminum, so they suck up heat like crazy. They're hard to melt. They did some chemical injection, and it was basically a total fail. They injected various corrosives, and the hard disks are quite chemically unreactive. And then the most fun they had was with physical tools. They used a lot of woodworking tools, such as hole saw, spade, bit, and grinding disc. And they got things hot and burned themselves a lot. You should definitely watch the talk. I was going to say that earlier. I don't want to say too much about the actual talk. Just go online and watch it. It's very, very amusing. And then they did some electro-deplating of the platters, which worked great on the glass platters, completely failed on the aluminum ones. Just a word on how they destroy drives industrially. When they decommission disks, They mostly degauss them and then throw them into a shredder. I was going to turn the sound down on that, but I forgot. Sorry. So when you're getting rid of drives, you want to predict your adversary. The TLAs are able to collect and exploit physically destroyed drives. I talked to a guy who did EOD work in Iraq, and he was under instructions from the NSA that if he found any hard disks that were not crushed and burnt, to send them in. They could get stuff off them. So if you want to nuke a drive from orbit, degauss it, crush and shred, and burn. So here, since I'm in the 101 track, even though this is mostly original research, here is my 101 slide. So for anyone who's here actually for a 101 talk about how to destroy their own hard disks at home, you can leave satisfied after this slide. Open your drive, usually takes a Torx T8 bit. Remove the platters, usually takes a Torx T6. Rub it with a rare earth magnet to degauss it. Crush, break, deform it by the method of your choice. Then burn it. Then separate the debris, and don't dispose of it all in the same place. Separate it and throw it away. All right, so the rest of this talk, hopefully interesting to you, not necessarily useful. I, too, decided to use 3 different techniques with this. So thermal, kinetic, and electric. So the goal of doing a thermal method with a drive is basically to exceed the Curie point of the magnetic media. So for cobalt, that's 1,115 degrees C. At that point, it becomes magnetically disorganized, and theoretically, nothing can be read from it again. Here's some things that I didn't do, so that you can either try them or realize why I didn't do them. I really wanted to look at some flameless chemical reactions. I couldn't find any that got hot enough. Of course, you can make a kick-ass oven and bake a disk. That is not exciting to watch. You can inductively melt aluminum very easily. You can get a big inductive furnace. It's nice. I've used them before. I would have liked, I guess, to drop a hard disk in one and watch it melt, but I didn't do it. So, method number 1, the good old plasma cutter. So starting off keeping things simple. I've used plasma cutters many times. I expected it to make much more of a mess with a hard disk, but as you can see, really nice. It completes in about 40 seconds, and very, very easy to contain. You could build an array of plasma cutting heads that would match the disk. So looks pretty good so far. Oh, this drive is powered up and spinning. I wanted to see if it would keep spinning, and so just one insertion point would be enough to destroy the top platter. It'll start to leak out a little bit down the bottom to let you know that it's done. Very nice. This drive stayed hot for a long time. So this shot is after I repeatedly burned myself taking out the screws. And you can see that it has, killed some of the top of that platter. Here's a close-up shot of it. So it spun for a little while, but not for very long. It thermally seized up quickly, and there was some damage to the top of that platter all the way around, but then it stopped and it just burned a big fat hole through there. And if you look at the lower platters, then the hole went through, but they're not damaged anywhere else. So you can't rely on the drive spinning for this method. You have to have multiple cutting head parts. So that's the fully disassembled thing. Didn't make a lot of a mess. Totally feasible, in my opinion. Next, I thought, well, these guys use propane torches and MAP gas and so on in the previous talk. What if we could just use the drive itself as the fuel? Like pump oxygen through the drive and start it off with a little magnesium or something, and just see if the drive will consume itself. So here's oxygen injection. 3, 2, 1. I drilled a little vent hole that you can see venting out there. Eventually, I melt the oxygen hose and had to turn the oxygen off. So it didn't really go to completion. Here's a high-speed shot with the FS700. Is it going? No. There we go. So, little bit of a containment issue, but I feel like I could easily figure out an engineering solution to this with an extra 2U of insulation and air extraction. That's what it looked like before opening. And inside did make quite a mess. This was, there it is after cleaning off the platter, and you can see the platter is like nicely melted on one side, and I feel like with some more engineering effort here, just pumping a lot of oxygen through this narrow one-use space, that I could make this consume the whole drive. So I'm going to call that potentially feasible. But I know what everyone's here to see, and it's the first thing anyone ever talks about when they talk about drive destruction, which is thermite. So what I really wanted to do here was create a slurry thermite that I could pump into the drive when you push the switch, and it would just really fuck it up big time, right? So I experimented with doing some slurries. First of all, since this is 101, here's the thermite reaction. I know you all know this. Iron and aluminum swap their oxygen partners like they're at a swingers party, and it releases a lot of energy. You can get it up to about 2,500 C. 3-to-1 iron oxide aluminum by weight if you use iron 3 oxide. So here I am stirring up a slurry. It looks really nice. It's like very, very smooth and gooey, and you could really easily inject it. So I thought this was great. But in retrospect, the bright silver color that you see there, right? Remember, it's like silver aluminum plus red iron oxide. I should have clued me into what was going to happen next when I tried this. So here I am trying to set off the slurry thermite with a blowtorch, and you can see this is 8 times sped up, right? So it's really not reacting very pleasantly. It's not helping me out at all. And so my theory is that the solvent is forming micelles with the oxide inside and the flake aluminum sticking on the outside, and it's just preventing them from reacting very well. And I tried a bunch of different solvents, such as glycerin, petroleum naphtha, and kerosene. And you can see afterwards, if I run a magnet over it, that very small amounts of elemental iron are being produced. Not very much at all. So the reaction is just not really happening here. Probably the oxide is just being blown out with the smoke. And when I flip over this top that I was burning it on, there's no damage to it at all. It really didn't get hot enough. So total fail. So next idea was, well, if you open a disk, there's quite a lot of space inside it. So, if we were really paranoid running a data center, we could hide thermite inside our drives just for when we needed to use it. So I pulled off some unused pins from the disk bus connector to use as an igniter, and I found that you can fit about 15 grams of thermite inside a drive. And you can still, the heads don't need to move into that space. You can still read and write to the drive with that in there. So this kind of thing always makes me feel like some kind of sketchy drug dealer or assassin when I do this. But it really makes me laugh because, when you go through the airport and they make you turn on your electronics, totally worthless, right? There's plenty of room for destructive shit inside electronics that still function. So here is the shot with the pre-inserted thermite. 3, 2, 1. Not too bad, right? We can deal with this inside 1U. But we open it up, and you can see that a lot of stuff has burned, and there's stuff all over the platters. But a little closer examination here, we start to see the nice, shiny, non-stick, chemically unreactive platters coming through. And when it's completely washed off, actually, bugger all has happened to those platters. Total fail. So, all right, I wasn't ready to give up yet, and I know that in military thermite grenades, they actually don't use straight thermite, they use what they call thermate, which is 70% thermite and 30% barium nitrate. And what the nitrate does is produce extra gas to move everything around and spread it around, and it also burns hotter. So here's 15 grams of thermate inside a gun. Much more violent, as you can see. And here is a high-speed shot of that, just to titillate everyone. The top of this drive, by the way, is screwed on really hard, but that doesn't matter for the thermite. It's happy to pop it open a little bit and spray out like crazy. Actually producing much more sparks and debris and so on than the plasma cutter. But, we could still probably deal with this if it works. This just goes and goes and goes. Don't remember the frame rate this was shot at. Probably 240 or 480. Anyway, that happens for a long time. So carefully opening it up with a glove this time.
That actually did pretty good, huh?
Yeah, that's quite impressive compared to the straight up thermite. I guess there's a reason why the military uses this formula.
So I had high hopes. I was happy. Taking a closer look at the platter, there's all kinds of crud all over it, and molten iron has been spread about the place. And then when we clean it off, though, we see some good things. There's some iron that's like attached itself, welded itself to the reed head. We got some pretty good heat deformation of the platter there, and we've welded the platters together over here. But ultimately, most of that platter is probably still recoverable by electron microscopy techniques and stuff like that. So once again, fail. Well, there are other types of thermite. For example, copper thermite. So exactly the same thing happens. It's copper oxide and aluminum. The oxide switches over, 4.4 to 1, copper oxide to aluminum by weight. It's a very aggressive thermite. So let's see what happens when we stick as much as we can of that. First of all, so I thought, wow, that stuff rules. Like, that really surprised me how fast it went. So like maybe the slurry will work with this stuff. So I made up one of the best slurries and blowtorched the shit out of it. And it burns a lot better than the iron thermite slurry, but still the reaction is very much retarded by the slurification agent. Anyway, so let's stick some in a drive, not slurry version, and see what happens. We can work on the drive delivery mechanism some other way, maybe. This is another high-speed shot. So keep watching, because once again, the lid of this drive is really screwed down tight, and you'll see the lid exiting stage right. But keep watching, because you will also see the drive eventually coming from somewhere airborne. So this experiment coated most of Miles Sledlip's workshop in copper. So everything in there now is going to have excellent conductivity. So that's the inside of the top plate. You could really make some nice art with this technique. So I'd like someone to tell Eddie the Yeti to really go and kick things up a notch over in the vendor area. And that's what the drive itself looks like. And you can see it's really got everywhere, as you would expect from that shot. And looking closely at the platter, you can see that it's stuck a lot of things to the platter, and you can see elemental copper has pooled all around the drive. Looks pretty nice. So let's wash it off and see how things really look. Yeah, boo to you, copper thermite. Some of it stuck, right? Like, it definitely made a bit of a mess, but ultimately, we have to say, infeasible but fun. So, all right, time to get serious here. And I thought, well, the way that people really talk about thermiting drives is they get a whole bunch of thermite in a crucible above the drive and just try and melt straight through it. So I thought, well, let's see if we can do this in 1U. So I built a ceramic mold that would fit in 1U if I'd made it a little more carefully. 250 grams of straight-up iron thermite. So what I did was, use a piece of styrofoam to fill the interstitial space in that ceramic material, made it matched exactly to the drive so I could clamp it on, and there it is, the hollowed out, all that area filled with thermite. So let's see if that's enough. So as you can see, my careful containment worked perfectly. Incidentally, Miles Sledlip's workshop has a large area rug on the floor. This shot set a significant portion of that rug on fire. So, sorry, Miles. Well, you know, that looks so impressive. Surely there can't be too much left of the drive that we just did that to. Once again, I'm now taking no chances with how hot things are after doing this stuff. So we can see plenty of elemental iron that's pulled into little nodules and clumps on top of the drive, and it's made its way through the top of the drive, through that little hole there. And inside, it's certainly made a mess of the drive electronics, but I've already brushed that with my finger, and I've seen that, yeah, there's still plenty of nice, clean platter in there. Look at that. You know, it looks almost good as new. So, unreliable. So next time someone says, oh yeah, like drive destruction, thermite, no problems. Just remember that they're a huge heat sink, and you'll need a lot of thermite to do it properly. All right, moving on to part 2, kinetic. Goal here was to deform, spindle, mutilate the drive, basically severely retard any form of mechanical scanning to be done after the fact. And so obviously, as I said at the start, that would have to be used in conjunction with degaussing. Degaussing is not fun to watch, so I did not do that. I had a bunch of ideas that I didn't do all of them. One was to do a horizontal hydraulic crusher that would fit in one U and like just squeeze the drive to bits. I was pretty sure it would work, so I didn't bother doing it. I wanted to use some other high-pressure cutting tools, but again, you know, that was just for fun because it's, you know, to build a water jet cutter into your data system is, you know, just probably a little bit infeasible. Instead, I wanted to start off with some like percussive methods, and one of the tools that I've used a lot in my place is this concrete penetrating nail gun. So it uses a propellant charge, basically a .22 caliber blank, to drive nails into concrete. This happens so fast that at 480 FPS, you can't even really see the nail. It just is long gone through this cinder block. Here's another shot with this. You have to hit it with a hammer, this particular tool, to make it go, which is, you know, you have to do something a little different for actually doing on hard disks. But you can see there the plastic sabot that holds the nail in the barrel fly out, and the nail kind of slightly can see it. So I milled the end off a drive so that we can see what happens while it's spinning, and we hit it with the nail gun. Boom. No problem at all going through the cast aluminum bottom of the drive and through all the platters. It actually cracks the cast aluminum drive part. There's a close-up of it, and you can see that it's, you know, you could build an array of these things that just punctured the disk in multiple places. So I think totally feasible. We also had around a pneumatic nail gun, and I didn't have high hopes for the pneumatic nail gun because it didn't involve any form of chemical propellant or explosive. So I'm like, you know, how good is that going to be? But let's give it a shot anyway. I didn't even use a new drive for it, right? But it turns out it goes straight through the fucking drive. Really nice. And so it uses like a big flat pancake cylinder. So the one that's on this particular nail gun is big, but you could quite easily build a low-profile pneumatic cylinder that would fit in your extra 1U that you have according to these rules, and just punch through the drive in a whole bunch of places. So quite nice. There's a close-up showing that those nails just got all the way through and out the other side. Again, totally feasible. So Thermite 0, nail guns 2. But this is what we're really excited about, right? This is why we came here. There's no doubt that we can destroy drives with high explosives, all right? And we also get thermal factors as a bonus. We can do explosive welding. So the goals here really, for me, was, all right, let's see if we really could confine this explosion to the rack equipment. And I personally had been wanting for some time to experiment with some new techniques. A binary liquid explosive and 3D printing shape charges. And then another sub-goal here was for me personally to pass go, collect $200 and not go to jail for this. So, let me introduce what I'm calling Felix. This is a commercial high explosive liquid binary. It is expensive. I did not want to pay for it. So I decided to clone it. So I'm not going to say its real name, but it rhymes with Felix. And I'm calling it Field Expedient Liquid Explosive. It's very similar conceptually to tannerite and Kindpack, which is ammonium nitrate and aluminum powder as a sensitizer. I reverse engineered it from the commercial product. It's based on nitromethane, and you use, as a sensitizer, stearic acid-coated 5 to 50 micron aluminum. So that means these individual components are simple to ship. They're just hazmat. They're not explosive until they're mixed. This is the stoichiometry. I still don't know the ideal ratios, but that's the reaction. So the nitromethane is the high explosive. It decomposes by itself. The aluminum acts as a sensitizer, but the aluminum then is consumed by the water produced by the nitromethane decomposition. So it adds energy to the mixture. So, all right, the legal thing, right? So I thought that with my friends who have a federal high explosives manufacturing license, that we'd be all set, because they have possession licenses, they have high explosive manufacturing. It turns out, we found right before we were supposed to do this project that it's not just the feds who care about this shit, and you have to get a state Type 2 license as well. So we were like, oh, fuck, right? Are we going to be able to do this in time? We just managed to get it done in time. So we were all legal and legit, and we could do this stuff. The big thing that we needed in the end was to have a range where we could do this, because the state wants to inspect your manufacturing facility. And we said, well, you understand what's going on here, right? This is these two things, and wherever we mix them, that's the manufacturing facility. Too bad. They want to know where you're going to do it. So we ended up very, very luckily finding a local bomb squad that would let us use their range. So that was really nice. And as a result of all of this stuff, my friends and I are actually forming a consulting group, so a little plug here. If you want to ever do this kind of work, then talk to me, because we can now do it, and even though it's kind of regulatory hell, being in regulatory hell is better than being in prison. So the stearic acid turns out to be a really important component of this explosive, and if you don't get that amount right, it doesn't work. So this is a test shot using a pyroaluminum powder with its stearic acid coated, but not that much stearic acid. Here's a high-speed shot, and what you'll see there, the blasting cap just throws it around. That is a non-detonation, right? So that is a total fail. When you get the stearic acid content approximately right, this is what it looks like. So I'm sure many of the people here already know this, but this is 101. So let's talk a little bit about the Monroe effect. So that's that's the official name of the effect when we say a shape charge. What it means is you have a groove, often conically shaped, but it can be linear. For example, like a cutting charge in your high explosive. So when you put that with the groove facing the material you want to cut, and you set it off, the cavity concentrates the shock wave and forms a kind of a jet. And you can actually line the cavity with copper or tantalum and form a liquid metal jet that will cut through whatever you're trying to cut through. Very, very useful technique. A lot of anti-tank warheads and all that kind of stuff uses it. So here are a few design tips for doing it. So what I was doing was I was laying out a cup to hold the Felix in OpenSCAD, plug for OpenSCAD. A few rules of thumb. Apex angle should be 40 to 90. The narrower the angle, the greater the penetration until your jet collapses and doesn't work. You want to stand it off by about 2 to 3.5 cone diameters, and your explosive charge height should be a little bit more than the height of the cone. So first of all, what I thought was, what about doing a linear shape charge in the shape of a ring and putting that on top of the drive, and so you cut through the platters. So I designed this also to fit within 1U. So there it is, viewed from the top, 3D printed, and viewed from the bottom. So we can fit 60 grams of Felix in this little container, and using a plastic cup there for the standoff. don't concern yourself too much at this stage with the containment, because I work on that later. This is shot at normal speed and then just slowed down. Here's another shot, same technique, same amount. You can see a bit of that drive exit stage right. Here's the results. So not as impressive as I'd hoped, unfortunately. The first thing you'll notice is there's a lot of unconsumed aluminum. So that stoichiometric mix was not correct. That was over-aluminized. Turns out, you don't need too much to sensitize the nitromethane. It stripped all of the platters off the spindle, which is pretty cool. And it has crushed the platters in amongst themselves. So, definitely has done some damage. Definitely would be difficult to exploit information to this drive. And there is one place where the shape charge has done its job and it's cut through, but that corresponds to where the cap was placed on that shot. So basically, we're doing the right thing with this charge, but we're having a problem capping it because the charge is not propagating around the ring the way that we want it to. So I thought about another idea. What about if we make our shape charges radial, coming out like that? So here's another OpenSCAD model. And also, to try and stop everything from flying around, we found a lot of aluminum around the place with those shots. I made a lid for it as well, with a little hole to feed some det cord through. So there's a 3D printed charge. 100 grams of Felix this time. It's a bigger physical thing. You can see the det cord that we're using to set it off all around the place. 18 inches of 80 gram det cord. Where did it go? This particular camera, by the way, that's the close camera. It's inside an ammo box with a 1-inch acrylic window on it, but you can see it gets a good shake from the shockwave. This is from a GoPro, 120 FPS. And you can see bits of that drive go in all directions. Nothing very big. So we had to search a bit to find the pieces. This one is interesting because all of the surface mount components have been ripped off the board. Here's part of the platters. Some more of the platters, and we've actually got some explosive welding happening here. That's actually the top plate and the platters have been welded together. So very nice. So that made us think like, well, let's try and do some compression welding. Let's actually just try and exploit that alone. So this is just a straight up det cord shot, 100 grain det cord in that top one, and then the double-sided version, doing some on each side. So to have the shock wave move from the outside in and compress everything together. So I'm going to show you the single shot later on because we did another interesting experiment with that at the same time. But this is the double shot. That's how we set it up. So actually, the drive is not in frame anymore, but it didn't move very far. It was actually quite well balanced. Here's a slowed down shot. Is it playing? No. There we go. So you can just see it just hop, actually only a couple of feet, but it's a sloped piece of land there, so it just drops down to where you can't see it in that shot. There's the drive. That's still got the plates on it. When we took that top plate off, you can see it did not strip the drive off. Oh, so this is the number one shot. This is the single det cord, so it's not the shot we just saw, but it's the number one shot. It didn't strip the platters off the spindle like the Felix shots did, but it did compress together them very, very nicely and explosively weld them. You can't see because they're welded together, but you can see that the reed head is welded to the top platter. And this is the double shot. didn't do nearly as much damage. I mean, okay, so the single shot is 2.5 times the double shot in terms of total explosive weight. So this is 40% of the charge of the single shot. It did deform the platters quite nicely. It made this like really cool groove in them. But we can see here that they were not welded together in any way, shape, or form. This is a Seagate drive, by the way, so it just goes to show anything you do to a Seagate drive doesn't work. But we do know that the charge that we need to use to compress the platters and weld them is between those two levels somewhere, right? So they taught us something. All right, moving on. The bomb squad said to us, oh, by the way, we have hundreds of these oil well perforators that we want to get rid of. Would you like a few? These are like downhole perforators. So, they drill the well and they stick a pipe down it, and then when it's all done, they put a pipe with these things on it to blow holes. So basically punch little holes through that pipe and through the concrete surrounding the pipe and let the oil in so they can suck it up, right? So they're designed to go through steel and a foot or so of concrete. And so to paraphrase Ghostbusters, if the bomb squad asks you if you want to be friends and share their stuff, you say yes. These are set off with det cord, so they're full of like a very fast high explosive, like maybe HMX, and there's just a little bit of foil at the top to let the shockwave through, and then you can see here the classic shape charge, right? So you got your conical cavity lined with copper, and this particular one that I'm pointing to there has a standoff so that it's just, everything is right for it to cut through things. So here's a shot we did with 2 perforators pointing up. Just to get rid of them at the end of the day, actually. But I want to draw your attention to a still frame from that. Right? So you could never get this shot if you tried like 1,000 times at 30 frames per second, right? These are the jets from the perforators. That's the blasting cap. The shockwave has gone through the det cord, set off the shape charges, and it hasn't had time yet to break through just the plastic shell of that det cord, right? This is a miracle still frame. So here's how we set it up. On the edge of the drive to see how much we can cut through. Here's the shot. So, B camera shot. You can see a chunk of the drive go flying off top left. There you can see how it just basically cuts straight through the cast aluminum casing. Here are the platters. Straight through. There's all the bits we could find. Some of it went in the water. But wait a second, down the bottom right, what is that? That is where the drive was sitting. That's a hole through the 1/4-inch steel plate underneath the drive. That's the exit hole on the other side. That's the hole it dug in the ground. And that's the piece of wire we used to measure the hole. 15 inches after going through drive and steel plate. Yikes. So the bomb squad was interested in that. They brought, the next time, the smaller version of the oil well perforators. Once again, a Seagate drive. You'll remember these 1.5 terabyte Seagates if you do anything with disk drives, because this is when the Asian tsunami happened and quality control went through the floor because all the facilities weren't working, and so every single one of these Seagate drives failed, if you look at the statistics. So this time we're going to do 2 perforators coming in at 90-degree angles. See what kind of results we get there. And this time lying the drive down. This time we brought the FS700 so we could shoot at 960 frames per second. So you see a bunch of drive exiting to the top of the screen. You get more of an impression of that on this wide shot from the GoPro. So they're out of the ballpark. We actually didn't find enough pieces of that drive to really draw too many conclusions about it. We found this much And you can see that the drive case just very nicely quartered like that. But we didn't find the platters. So we had to do the shot again. We were all out of 1.5 terabyte Seagates, so we used this one. I'm not removing the label from this drive, but I think I'm going to avoid its warranty anyway. And this time we put the steel plate on top to just try and keep the fragments to where we could find them. The GoPro shot is nice of this one. Just a little graceful, leisurely arc. So there's what we found of that drive in terms of the case. Did also a really nice job going through to the center spindle, and there are the platters. So we cut through the platters, but not through the spindle itself. So I feel like we could probably tune these shape charges to go just through the hard disk and no further. So I feel good about shape charges, but there's one other charge I wanted to try, which is a diamond charge. The EOD folks use these a lot for cutting. What you do is you create a flat, high explosive, and you cap it at both sides, and when you set it off, the shock wave comes in from both sides, meets in the middle, and turns 90 degrees. And you get a jet that comes out either side and cuts through whatever you want to cut through. And what I wanted to use for this was this stuff. It's data sheet. It's patent explosive sheet. It's kind of like a high explosive fruit roll-up. And I've used it before. And we had some. Yeah, all right. We had some, and I wanted to use this on the shoot, but it's difficult to transport. You have to be placarded to transport this stuff based on the original packaging. So no matter how much you actually have, it's just what's written on the packaging. So we had a small amount, but the package said was a huge roll, like a kitchen roll. And so we couldn't move it. We could get it, but we couldn't transport it. So instead, I 3D printed again a container and filled it full of Felix, and we capped it from both sides with det cord. So here it is set up, 60 grams of Felix, and there it is, good to go on the drive. And this shot, the diamond charge is underneath the big steel plate, and we were also getting rid of, again, at the end of the day, some surplus perforators under the big steel plate. That's a half-inch steel plate. So there's, I think, 3 of the small perforators under there. You'll need to know that for this video. So that's the big plate coming down. The heavy plate is not in that shot, but it is in this shot. Once again, this was, I think, our last shot of the day. So, wait for it. There's the 1/4-inch steel plate, and there is the half-inch one. So it's a good thing we didn't need that anymore, because it was gone. But there's the drive. It didn't actually do too much. It just acted like a platter charge. You can see the edges of the diamond in it. It didn't cut it. Total failure. Anyway, it was interesting. I'd like to try that again with the det sheet, because I know that works. So blast suppression, all right? We've had fun blowing things up, but can we actually make this work inside equipment? So we've got a couple to blast to the drive, but we want to decouple it from our equipment that we're storing it against. So we have the explosive against the drive and some kind of damping material between the explosive and the equipment shell. What are we going to use to damp it with? Well, it'd be great if we could get some kind of nice substance that was an alternating compressible and incompressible matrix, maybe like some kind of a liquid and gas foam. It'd be great if it was inexpensive and that we could actually inject it into the equipment when we wanted to, so we don't have to have our equipment full of foam. Where could we get such a wonderful, like, high-tech magic thing? Yes, thank you, Pyro. So we learned this from the explosive engineering instructors. They actually use this when they explosively punch out lock cylinders. So they'll put a big gulp cup full of this stuff over the explosive, and they'll punch out a cylinder, and the shaving cream damps the noise in the frag. So I said I'd return back to this shot, the single 100-grain det cord shot, plus the shaving cream, inside a box. Let's see how that did. You can see the A camera there, left of shot. So, all right, you know, this was a shot in which the drive was really shredded and stuff definitely flies everywhere. But let's take a look at some still frames from our 2 cameras on this shot. That is the first detonation frame of the shaving cream shot with 100 grain det cord. This is the first frame without the shaving cream from a charge that was 40% the size of the left one, right? So the left one's 2.5 times the explosive as the right. Here it is from the other camera. So if nothing else, we're definitely damping the flame and heat pulse that's coming out of that. That's really interesting to me. So we tried this again with a kind of a simulator of a 1U rack. So here's 75 grams of Felix. It's the annular shape charge thing again. This is our 1U rack simulator, the steel plate with the angle pieces welded to it, set up here, coated in shaving cream, and then with the other plate on top of it with a sandbag. So we're just kind of getting an idea about, you know, stuffing stuff into 1U and what's going to happen.
3, 2, 1.
So I personally think that's pretty impressive. Here's the FS700 shot. Like, stuff goes flying, but markedly different from all those other undamped shots that we did. Here is the steel plate, and yep, it made a dent in the steel plate. That's where the drive was, and that's the other side of the steel plate. So it was dented, but totally non-perforated. Here's the other one. Didn't fare quite so well. We did actually unfold the angle iron and split it a little bit. But you can also see the drive imprinted on the plate there. But there's the summary here after damping stuff. The high explosives, with enough engineering effort, it just might fucking work. So I have to go really fast now with electric. There's not too many things in there. The goal was, you know, we've got electricity already in the data center, so let's do it. And especially I wanted to look at SSDs. So things I didn't do: mass degaussing, boring to watch. I didn't want to put you through that. EMP microwave RF attacks might have been fun to do. I may do that later. First thing I wanted to do was exploding bridge wire. So here's our sketchy capacitor bank and spark gap trigger. This is how we charged up with good old-fashioned vacuum tubes. And I could not find anyone that had SSDs that were broken that they would give to me because they're just too new. And I'm sorry, I love you all, but I am too cheap to spend thousands of dollars on SSDs just to blow them up. So I'm used to using flash drives. It's very similar. It's just the SSD looks the same inside. It's just flash memory chips soldered onto the board. So I think we can draw some conclusions here. So here's what happens when you dump a lot of high voltage through a wire.
1.
Here's a high-speed shot of that. Happens very, very quickly. So first thing I wanted to do is just to physically couple that to a drive and see if we could just use the force of that explosion to destroy things.
3, 2, 1.
High-speed shot. So you can see in the high-speed shot that it didn't work, right? It didn't. There's nothing happened to that chip. Although, when we look at it closely afterwards, the memory chip itself fared just fine, but we did decap the microcontroller on the other side. That's actually blasted the potting material off the chip. But we cannot rely on this method. So what about if we have our drives in our data center and we're hooked up to power and ground and we can deliver a large voltage spike when we want to through like a spark gap or something like that? So I soldered onto power and ground with these flash drives. Here is the
3, 2,
real time. Nice shot. High speed. So we can see in the high-speed shot that we really did some damage there. And there we can see that we blew the flash memory chip right off the board. You can see all the internal leads from the chip. We broke the chip in half and decapped it. So nice lot of damage to that. The one thing we don't really know is how recoverable flash memory chips are when that's happened to them. Whether you can use microscopy techniques to get stuff back. But I'll say potentially feasible to destroy things quickly that way, at least to make it difficult to do a recovery effort on. For regular drives, that's an inductive deformation of a soda can. So you can wrap a coil around something metal and you can do a shot through it and destroy the hell out of it. That's 2,000 frames per second. Here's another shot of that. Obviously, there is a big difference between a soda can and a hard disk. This is at 100,000 frames per second. So you can see that this squeezes down very, very quickly. This is the other side. So basically, the whole time I've been talking over this slide, 10 milliseconds have not yet elapsed there. So you can destroy things really quickly. And it would be really great to destroy hard disks that way, but the necessary power levels to do it with hard disks are currently unknown. Maybe we'll do some real mad science later on. So here's the summary. The most feasible methods in each category. The plasma cutter worked great in thermal. Oxygen injection, I think, could be feasible, but maybe require complex injection. Kinetic, the nail guns were great. Damped high explosive was really fun. Possibly failing the seismic part of the rules. Oh well, who cares? Electric, high voltage power spike was good, but we don't really know the forensics resistance of SSDs. Number of eyes lost, 0. Now, just before the goon drags me off stage here, I just want to say one more thing. Mobile solutions, right? We've been talking about data centers, but when they picked up Ross Ulbricht, the Dread Pirate Roberts, they basically mugged him in a public library. They grabbed him, they dragged him away from his laptop, and it was unlocked, and they harvested everything that they needed to put him away for life, for federal crimes. So we can, these days, very easily, with commonly available open source hardware, develop systems that are proximity connected to our computers, right? So using Bluetooth or whatever. So I just want you to consider this. Feel free to come and talk to me about all your ideas for doing this later on, and then maybe we will make another DEF CON talk about this stuff another time. Thank you.